Right, good day. Let's talk a little bit about software and hardware interfacing, a fascinating topic, well, at least for me. But before we start, a fine gentleman, if I recall correctly, what was your name? Evan, right? So he was actually the first one to come here to this session, probably 20 minutes minus to the start of the presentation. So for such an interesting topic, you get a virtual prize. It's all yours. Right, we're talking about software engineering, virtual things, so therefore the prize is virtual as well. Right. So a gentle introduction to hardware. So first, let's start as we are in a software engineering conference. Well, there are multiple programming languages in discussion, but one of the dominant ones is C++. Where does C++ run? On an abstract machine. Have you seen one? Yes, it's an abstract machine, right? So it's the same thing as a spherical cow in a vacuum. But as you can see, a spherical cow in a vacuum, that means it exists. And an abstract machine, well, no. So in fact, C++ code runs on the actual hardware. So on a compute platform. And we'll spend some quality time trying to discuss what's there, how, only about a small fraction of the complexities there. Two parts, the memory system and the compute system. There's something in the middle which interconnects both of those and some of the components. We'll not go into that. Simply, we have only 1 hour, not 2 days for this. All right, so looking a little bit back into the history, at some point in time, compute platform and a processor looked like that. As time passed, it started to look more like this. Memory initially looked like that. Well, this is beyond my time. I actually have only touched such a thing, but haven't used it. Then started to look more simpler to the contemporary ones that we see, and then there's interconnect in the middle, and that's where those components lie there. So actually this reminds me of my happy childhood when I was learning by which end to hold a soldering iron. This is not the actual photo. The actual photo of the machine that was assembled didn't, well, actually, the board didn't live to this day, and there are no photos, so this is just, well, shamelessly borrowed from the breadth of the internet. If we look at the commodity platforms of today, they look mostly the same, just a little bit few more pins, both on the compute side and on the memory side, but the fundamental operations, they are mostly the same. Interconnect is far more interesting and far more complex, but we won't be looking too much into that. So, part one, memory. Memory, in fact, is nothing more than just an addressable capacitor array. So if we are looking from the, again, abstractized perspective from a software side, memory is just an array, addressable array of bytes. The way how those bytes are implemented in today's contemporary memory, it's a capacitor-based system. So basically a capacitor, an electronic component which is capable of holding a certain charge for some point in time. It's good for carrying 1 bit. If you need many terabytes of storage, you need a huge amount of capacitors. No big deal, except of the laws of physics, that you need space for them, you need power to feed those things, and you also need to be aware that a capacitor interconnected to all the sensing circuitry is actually a leaky thing. It tends to lose the charge quite quickly. We're talking about the order of milliseconds. An important aspect to remember when we are talking about practical engineered memory systems is to feed out engineering facts from the marketing propaganda. Speeds are increasing, at least in the marketing papers. Speeds in reality are not increasing that much because the laws of physics hold. You still need to use the same amount of time and energy in order to charge or discharge the capacitor to a certain level. So let's look at some timing operations of how the memory system works. You divide the array into a two-dimensional structure, rows and columns. You send out a particular command, how that is encoded on the actual bus does not matter for our discussion, but you send out a command, and suppose it takes one hypothetical nanosecond to be sent out from the memory controller side into the actual memory module. Then we have to wait for the logic on the memory side to do its part of the job. Then we send out another command indicating whether we want to read or to write from that particular row. And again, wait for another 10 hypothetical nanoseconds for particular capacitors within that row to be sensed and the data that is stored there to be copied into some temporary buffers. And then finally, we can transfer or read, basically transfer to or transfer from that address that we have selected, and that takes slightly less than we have waited previously. And then you need to return back the previous data that was there, because the read operation is destructive. The way how memory operates from a sensing perspective, it's very simple. You connect the capacitor to a differential amplifier, one input from a capacitor, the other from a reference voltage, which is half of the potential between the low and high signal, low and high levels, and you see what is happening. If the capacitor is discharging, that means it used to contain a high level. If the capacitor is charging, that means that it used to contain a low level, but you destroyed the level of the charge that was there. Therefore, you need to return it back. This forms a protocol, basically a signaling mechanism that needs to be sent out into the memory module and followed by the rather strict timing guarantees in order to be able to read or write something. Well, then you wait until the capacitor then is pre-charged to the levels that were prior to the read or write operation. One of the problems with this is right here. You spent on the order of, well, something like 40 hypothetical nanoseconds in order to transfer data over 1/10 of that period. It doesn't look too efficient. And here we are coming to an aspect of the memory characterization. It's a bandwidth of what you can transfer over a particular bus versus the latency, how long you need to wait until you get that data or you are able to send it out. In reality, things look slightly more complicated. There are two separate buses with two separate types of properties. One is used for commands. The other one is used for bidirectional data. They are not used at the same time, but they are synchronous. In a sense, commands cannot be decoupled. It's not something like an event-based system where you post a command, get an identifier for get, and at some point in time, you will get an interrupt or form of notification that your command is complete. No, you need to wait for a predefined amount of clock cycles in order to be able to transfer something in or out. And that adds up. We are talking at a resolution of a nanoseconds here, but that adds up. So important aspects when we say DDR, double data rate, we need to distinguish two large portions of this. One is the architectural concept, in a sense, what can be transferred at a double rate versus the clocking into, compared to the actual protocol. So basically the signaling mechanisms that we need to follow in order to get something out of the memory module. So only the small fraction is double data, and double or quad or octal. There are specialty memory types. The rest runs on the base clock frequency. However, marketeers are happy to tell you that it can transfer terabytes of data per nanosecond on a double data rate. No, that's not correct. If you're trying to measure the performance, you need to take into account the protocol specifics, and it is just not possible to achieve the theoretical limit of the memory bandwidth bus, just because of the protocol itself. Addressing is a two-dimensional, and that has impact into how do you allocate your objects in memory. We'll come to that at the second part as well, when we'll be talking more about the compute part. But purely from the memory layout perspective, It's not equivalent to think that basically it's incorrect to assume that all of the memory address is addressable in uniform time. It has a hierarchy, a rather strict hierarchy, and trying to align with that hierarchy or misalign with that hierarchy can have an impact to the overall performance of the system. Now, generation to generation, if we look for last, say, 20 years, the frequency at which the capacitor array operates hasn't changed much, if at all. What has changed, and noticeably, is the actual interface speed into the memory. So in simple terms, that means that latency has become worse and throughput has become better. Overall, it's a question of how do you balance from a software perspective and which parameter for you is more important from that perspective. Another important aspect is on the addressing granularity. You're typically used to 4 or 8 kilobyte pages from a software side. On a hardware domain, those numbers look different. It's half a kilobyte, 1 kilobyte, or 2 kilobytes, depending on the implementation details, and we will see some examples of that slightly later. You also need to be aware of the specifics of the platform on which you are working. So the main limitation: at one point in time, within a memory array, you can have one row open. One row, generally, that's on the order of 1 kilobyte. And that means that all the operations that you can send out rather inexpensively is limited by such a small amount. That doesn't sound too practical. Therefore, what can we do in search of a simple solution? Well, we can partition our array into subarrays. Right? Technical term for that is a bank. And one bank can have one outstanding operation at a time. Therefore, in this example, we can send out four separate isolated commands. Memory implementation, and the memory array implementation does its work there, and we get 4 sets of data portions coming out, interleaved via some way or the other. Now, from a practical point of view, it makes sense to have an ability to have certain operations applied to all of our banks. For example, a refresh when memory is not used. And remember, you need to do that every few tenths of milliseconds. Otherwise, due to leakage, you will lose the charge in the capacitor array. Then we can also, if we are increasing the number of banks, we can try logically increase the number of groups. Therefore, now, and this is a particular example of a DDR4, it can have up to 16 separate banks grouped into 4 groups. And that means one module, logical module, we'll come to some other groupings in a moment, can process 16 outstanding commands at one instance in time. Then this comes to a physical implementation, memory components, memory ICs soldered on the board. There can be multiple layers, multiple stacks of them. Think of it as a chip select line from Z80 days. You can have multiple ranks, which is also part of the addressing command. And then in total, DDR4 can address 34 bits in total summary, split to 16 banks and up to 8 ranks. There's a large amount of marketing differentiation. Some vendors implement in one way, some others implement in a slightly different way. There's also notion of the multi-layer or multi-die packages, which add in yet another level of addressing. Those are tiny details. What is important here is to know how your memory is organized from the physical point of view. This is an example of how you can achieve the same memory capacity per module, but with a different internal organization. So starting probably the most common one with the 1 kilobyte pages, built out of the smaller components having half of a kilobyte and the wider one of 2 kilobytes. From a software perspective, it's all invisible, except of the performance. What kind of performance are we talking about? In general, about few percent. if you care about nanoseconds from a software perspective and you count them, you will rather carefully look into optimizing certain things here. On another hand, well, we all know that P in Python stands for performance, right? So at that level, probably there's no point in going deep and trying to find out something and configure that. All of this is absolutely hardware dependent and platform dependent. Generally, you wouldn't have much of access to that from a perspective of trying to change that. You need to be aware and basically adjust your software side. If you are building your own platform yourself, certainly you are in control, and then you can tweak that to your particular requirements. How does this work in practice? Suppose you have a 36-bit address bus. This used to be true back in, say, Pentium 2 days with PAE addressing. That is split, so 2 bits indicate the actual socket, which will be, where request will be routed to a particular socket. Then within that socket, we have 34 bits, which are split into the rank, group, bank, row, and column. So that's kind of a hypothetical or theoretical distribution of the addresses. On the lower row, you see one of the practical implementations. Why we need such a mapping function? Remember from our diagram previously that only one bank can have the row open at one point in time. If we spread out sequential addresses that they map to different banks or bank groups, from an actual memory access perspective, we haven't changed anything, but from a timing into the memory system, we have changed, I cannot say quite dramatically, but noticeably. In theory, it can be, for DDR4, it can be up to 32 outstanding requests in one instance in time, instead of just one. How does that translate back into the absolute performance in terms of nanoseconds? This is the math that you need to do for your precise data allocation and precise how do you allocate objects to memory and what your platform does for the mapping. Some of them allow you some configuration. Generally, this is on a low level of, if you are familiar with the firmware internal, so this is controlled by the component called FSP, firmware support package, which generally is provided by the memory controller or processor vendor. And if you are building something yourself, you can certainly implement this to your specifications. Why this matters and what you can do about that? From a granularity perspective, from a software perspective, memory granularity generally tends to be seen in increments of cache line sizes. This is what you see from a perspective of how your code operates with the data. Eventually, after the hierarchy of caching, memory requests come to the memory, and that has different granularity. So the smallest row, depending on the components that can be used for that, might be half of a kilobyte. That means that if you physically spread your objects that you need to access, and here we are talking completely bypassing the cache. So if you need to access objects, say, more often, therefore, it would be beneficial to spread that at a granularity of intermixing of the rows. And the smallest practical one would be the size of the row. Therefore, you would be able, if you read if you try to access objects sequentially, eventually those requests will be mapped into different banks. The most say expensive performance-wise operation is sequential operations within the same bank. That means that you need to open a new row every time you have finished working with the current one, close the previous one, open a new one, and so on. If you have those scattered, you can have multiple ones open at the same time. How much does that save? Well, it saves one command plus the waiting time. We are talking on the order of, well, 10-ish nanoseconds. Does that matter? For some applications, that matters a lot. For others, in general, the answer, you need to do practical benchmarking. Not micro benchmarking saying that, look, my memory is twice as fast as yours. But a benchmarking which looks into the context all of your software stack operation, and basically that's an important and complex domain of itself. From a practical point of view, you won't have one extreme or the other. It will be something as a balance, and what you can do, you can tweak the parameters which allow you the scattering of the addresses depending on how you access, depending on your memory access patterns. So one concern voiced quite often to me about when talking about these topics is, so now if you pad your objects at a kilobyte boundary, so that means that you will wash out all the cache and that will have a detrimental impact. That's actually not true. The fact how that is stored at the last level memory and the way how that is stored in the cache is rather orthogonal. If your object occupies, say, one cache line, only that one cache line will be stored in the cache hierarchy. The rest won't be touched, won't be used if it's not touched. If your objects are large, eventually, yes, all of that, basically, the part that you are accessing will have to be loaded into the cache hierarchy, because that's the only way how the data can be accessed. But trying to align the data on the memory page boundary technically doesn't have negative impact into the cache utilization. Now, some open discussions about specialty memories and other domains related to the memory hierarchy. So you might say that we have heard this fancy thing, HBM, high bandwidth memory. It has that many thousands of bits. That must be way faster. Well, if you look from a technical point of view, that's not 1,000 bits. That's 8 channels, 128 bits each. So what does that mean? In order to utilize the bandwidth of HBM, you need to be able to send multiple outstanding commands into that. And the only benefit would be if you are able to load that from your compute platform. So if you, for example, are single-threaded, that will directly depend on how many memory requests you can send out. On the other hand, if you are a specialty compute platform, think of it as an accelerator or something like that, which can and is designed for issuing multiple memory requests, that's precisely the memory type that is for you. Similar kind of comparison can be said, for example, for the GDDR, the graphics DDR memory. It actually has the longer data transfer cycle. At the cost of slightly longer latency, you get twice the data transfer, which is compensated by the faster data bus. Overall, if you're looking from use case perspective, graphics accelerator needs to have access to rather large amounts of data. It does not necessarily have a very strict requirement for very low latency access, but it's more about the throughput. Therefore, a specialty protocol defined purely for such a use case. Talking about the remote memory systems, generally that's another protocol on top of the memory bus interface, and the complexity there lies in trying to do that in a cache coherent way. Again, can be solved from a software perspective, but you wouldn't be too happy if you would need to start to care about whether this particular object is seen in this particular version on this core and seen on a previous version on the other core. Therefore, the cost of remote memory systems comes from a cache coherency assurance perspective. There are specialty memory types, non-volatile, that operate something as a mix of a DDR protocol and a non-volatile storage. niche applicability. One of the practical use cases for that is a mechanism to store traces and debug logs. Suppose you're doing something, there's a triple fault, the machine goes to the reset and you don't have any logs remaining except of what has been written to a non-volatile storage. Restart, take a look at what you have there, and maybe there's a clue. From the contemporary compute systems perspective, memory system is the term to describe the actual protocol operations is the ANCO, as the memory controller sits there. And the cores that see the memory, they act as the clients. So one of the complexities in ensuring the efficient memory system operation is in scheduling. You have multiple cores, multiple requests coming into a shared resource. How that is allocated and shared between all of the possible clients, including the complexities like you can have a multi-socket system. You can have different types of memory, say volatile and non-volatile. They have very different timing parameters, but they operate on the same bus. Therefore, that's basically a complex task to try to achieve certain level of fairness and resource guarantees. And to add on top of that, there's a caching hierarchy. Which for efficient operation requires certain signals to be fed back from a memory system. For example, how many requests outstanding from what particular client and so on. And to use that as a hint whether this particular line might be needed at a future time, can be evicted and so on. Moving to the second part, the processor. It's actually much simpler. You have something that consumes memory from two directions. One for storing the data and doing something on that. The other is for getting instructions what to do with that data. Well, simple as that. We read memory from both sides and we do something useful. So if we now try to look a little bit deeper of what is happening inside from a logical point of view, well, basically what hardware does in order for the software to function. First, in order to do something useful, you need to have instructions. Therefore, you need to fetch them. And fetching instructions linear is trivial. You just read the portion of memory, send it out to decoders, and then the rest happens. The interesting problem is to be able to feed the instructions non-stop when you have a nonlinear control flow. So suppose you have a branching and you are not yet certain whether it will be taken or not taken. Or for example, you have the incoming branch. Basically, the control flow is coming to you and you need to be able to fetch enough of instructions to be able to feed the later stages without possible blocking. Then you might have cases where there are certain, say, sequences of instructions which logically do something combined, like a loop. You decrease the variable and check whether that is 0. So technically those are two instructions, but from the actual execution perspective, it kind of asks for to be treated as one instruction. Of course, we logically do some things that are very, very much combined. There are other such cases, and the technical term for that is fusion, where you can logically combine certain incoming instructions and later they are treated as one. Why? For a very simple thing. Instead of executing two instructions, you can execute one, although more complex one. So fetching is controlled by the branching logic. In essence, that's just a set of tables carrying various forms of signals that provide input into the fetch block from where next to load my instruction stream. And that's one of the two most complex components in each in the contemporary compute platforms. The other one being for the register allocation and basically out of order disambiguation. once we know what to fetch, we start reading from memory and start analyzing the instructions. It's actually quite a simple process. You read a sequence, you decode that sequence, and send it out. And well, software domain is inherently serial. You have a sequence of instructions and you execute them sequentially. The hardware domain is the opposite. It's simple and kind of natural to do things in parallel. I can take a block that looks like a sequence of bytes and try to decode that in parallel. Of course, if the instructions have a certain level of regularity, it doesn't matter whether if I start from a first one or from a subsequent one, eventually I will come to the same conclusion. And this comes to the first widespread myth. Now, you might remember x86 is a variable length instruction machine. Right? Therefore, instructions can be from 1 up to in practice 15. In theory, it might be, if my memory serves well, 22 according to the encoding rules. But it's basically a variable length instruction system. So how can I decode something in parallel if the instruction length is different, non-uniform, and not necessarily known in advance? Well, let's try and see. Anyone willing to? What's that? Right? Okay, let's see. So. And by the way, here, basically stepping aside, I will explain this in a serial format, but this is happening actually in parallel. Then we'll rerun this example again to see how that can work. Instruction decoder is nothing more than a pattern matcher. That's it. So you fetch, this is something like 20 octets, and you have 20 comparators looking for particular signatures. In this case, C3 is the red instruction, right? So each of the 20 incoming bytes is compared being equal to C3. 2 of them match, right? So there are basically 2 signals out of that indicate that this is a potential return instruction. And this is applied for other patterns as well. So you have a large set of pattern matches that operate in parallel, not sequentially. So C3 and FFC5, those are 3 separate patterns, and those are executed in parallel at the same time. Then you get match signals. Those match signals are fed into, think of it as a priority encoder. So if this particular signal matches and that particular signal matches, that means that the second one is more important than the first one, or the first one is more important. That is depending on the logic. So, continuing with this example, we have matched a few patterns, a few more, and what happens here? On a blue C3FF, we have matched one particular candidate instruction. Then on a light yellow, we have matched something else. And that actually overrides the decode of the blue part. And if we go a little bit further to the right, there are prefixes. And again, prefix overrides the instruction. In summary, we have decoded which initially started to look as something completely different as one final instruction which looks like this. Inside, as a payload of the immediate, it carries the bit sequence which looks like a valid instruction as well, right? But due to the priority and the outermost priority wins, we have decoded that to instruction that starts at the leftmost part. Continuing with this on the other side, that's how the prefixes work. So, and this is a really simple part. You scan for certain patterns. If that's identified as a prefix, simply remove it and modify the outcome of the adjacent decoder to mean something else. That's basically same pop instruction, but different register used for that. And if you look into the encoding tables, that's just one bit which is different. Technically, that bit can be fed straight from the decoding pattern matcher into the end result. Now, another one, prefix, which modifies things a little bit. Then you look into some immediates and you get the output. So this is the decoded output of this code stream. Now, if we go back So all of these functions of different colors, they happen at the same time. And if you look from top to bottom, that kind of maps into the logical propagation. You can think of it as a separate cycles within the decoder stages that we try to do this. We got the results in parallel, a multitude of them. We take the next one, we got another set of results, next one, and so on. Can the decoder be implemented purely in combinational logic? In theory, yes. In practice, also yes. This all comes down, well, you might have heard the term the number of cycles. Like, for example, multiplication instruction takes 17 or whatever. That's just a random number of cycles. First thing, you need to look into the overall context. The instruction doesn't take 5 or 17 cycles. It takes much more, like 30 or 40 if we are looking into the whole pipeline, but only the execution part takes that. Exactly the same is applied to the decoders here. If you have intermediate steps, you would need multiple cycles for that to process. However, if you have enough of a timing budget for all of your, in this particular example, comparator signals to propagate from top to bottom and resolve all the conflicts and do all the priorities, another conflict resolution there, you can do that within one cycle. However, the time interval, basically the clock rate for that cycle, will be practically low. That's just a normal engineering trade-off. You need to do more logical work for that, therefore you need more time, therefore your frequency goes lower. In fact, having more intermediate steps, having the decoder that occupies several cycles time-wise, will result in faster overall decoding system. Because you will do a large amount but shorter logical steps. So, decoding x86 is simple, and in fact the reason for that is straightforward. x86 has a regular structure. Well, it might not look from a beginning. However, if you start looking into the instruction encoding tables and the rules, how those instructions are encoded, well, things are quite obvious. Just draw that in 2 dimensions and you see that the same bit pattern repeats and repeats, right? It's only the prefixes and well, other indicators that indicate whether that it has a modern byte or immediate or something like that, that modify the instruction stream. But the actual instructions are simple. So, after the things are decoded, they are fed into, well, the queue. Also, there's a concept of the cache. If you have a loop, decoded instructions can be reused. And one word about what do I mean by decoded instructions, and I might use the word operations quite interchangeably. The x86 encoded instructions is just a contract, nothing more. So basically, it's a universal interface which is accepted by the x86 platform to feed your intent. I want you to do this. How that is executed internally as well, generally nothing in common of what is being fed from the software side. That's purely an internal implementation. It differs from generation to generation and quite noticeably. And that's basically the internal representation of how do you activate certain signals to notify the particular logical execution units to do something. Right? It has different registers, it has different identifiers, it has different commands that don't directly map to what is visible from an external side. It also has cache for certain reusable code paths. It also has another big myth, microcode. Oh, the big evil microcode thing which does bad things. No. That's just how the platform operates, and microcode and micro operation stream coming from a decoder is exactly the same thing. The difference is that normally decoded or simple instructions get translated into a sequence operations that gets fed later. If a particular instruction decodes to a pattern that indicates, well, basically it's a complex instruction, like for example, AO ports, first that comes to my mind. That simply indicates now you go to this offset in the microcode table and read from there until the end, right? That's just another source of where you get the operations, which go to the same queue, which go to all the subsequent operation execution units. Now, another myth about x86 and another architectures. Code density. So you have this hypothetical C code, well, for all the completeness, you should have the volatile code word there in order to really compile into what is shown here. But that's basically the output of on an x86 platform. I have an immediate value, which is 8 bytes, and I have a few bytes for instruction. That's it. Basically, it loads an immediate value into a particular register. Let's look how the alternative reality can do that. Take a look MIPS. One of the problems with that is that it has a fixed 4-byte instruction length, right? Well, regardless how hard you try, you cannot fit 64-bit immediate into 32-bit code word, and even some bits need to be reserved for the actual operation. Well, what you do what the only option that is available. You split that into logical operations, load it by bit portions, and then logically combine that, right? It does the job. However, that occupies, if I'm not mistaken, if I counted correctly, six operations and the whole 24 bytes of code space. Another alternative reality, the fashionable RISC-V, does exactly the same, just encodes a few bits in a different way, and the constants are slightly different. Depends on the compiler, depends on a lot of other things. Now, the historical Spark does precisely the same, again with a slightly different implementation, and then there's ARM. Well, ARM, they probably came a little bit more prepared to this problem. They said, look, this is an often used operation, therefore we need to optimize at least a little bit for that. Well, it's 4 instructions instead of and 16 bytes. Now, where's the problem? Contemporary platforms, or performant platforms, they look into the stream of incoming instructions, they do pattern matching there, and certain patterns that match can be logically merged, and therefore it results in a few operations out of the incoming instructions. Now, if we are left for the freedom of the compiler to generate various code sequences for doing instructions that don't fit into code word, this complicates the pattern matching a lot. And generally, that is one of the reasons why one of the 2 main reasons. So one being the complexity from the incoming instruction stream, that it is far more difficult to try to guess what each particular compiler and release of the compiler, depending on a lot of other circumstances, generated. The other thing is basically about the whole performance. If you want to have a performant compute platform, you build it for, basically you need to design a performance system, and that takes 2 parts. One is actual implementation. If you want to have a fast multiplier, you implement it in a fast way, right? Therefore, it will be a large area, wide implementation of a multiplier that requires noticeable amount of power, but it will be a performant one. If you care about not the, basically it's a balance. You either care about the performance or you care about the efficiency. You can implement the same multiplier as a multi-stage one. That will take proportionally more clock cycles. That will occupy less area space. That will consume less energy to operate, but the performance will be lower. Therefore, if you build your software ecosystem in a way that can feed mostly random sequences of instructions, you don't expect that the hardware will try to adjust to that and will build the equivalent amount of logic inside to try to detect all of those logical systems. kind of the derivative out of that is if you care about the performance, you don't do things like that. You better fix the ISA, your instruction contract. And one of the problems, and then we will continue. Yeah, all good, thanks. Right, so the problem with instruction length of RISC-V and ARM, instead of making them shorter, you need to make them longer. Because loading large immediates is rather important and frequently encountered operation. Trying to save 2 more octets and have the complexity of figuring out when where to return, at what alignment and so on, it might be worth for a controller which controls the LEDs on your washing machine, right? But if we are talking about a high-performance compute platform, that's certainly not an area of concern. Fusion. Again, looking into some sequences, taking 2 paths to the previous example, x86 and ARM. Eventually, inside of the machine, that translates into something like on the last line, and I kind of named that as an imaginary ARM, because eventually within the further execution pipeline stages, it looks like that. So you take multiple instructions, or one level lower, multiple micro operations, and you fuse them, combine them together. You basically reduce the amount of actual work that needs to be executed as a standalone entity. That means that this particular operation will have more things to do, right? But from the perspective of the work unit, you have reduced the amount of work units that need to be sent further. The next one, and one of the complex parts of the contemporary compute platforms is basically preparation for the out-of-order execution, allocating the internal representation of registers that you have fed in as a contract into how that will operate internally. Basically, it's trying to find, to deconflict the data dependencies, saying that this particular sequence of instructions, they operate in isolation, and this particular sequence of instructions operate in separate isolation. Therefore, they can be executed in parallel, provided that they have enough of the capacity to run them in parallel. Then there's when the conflicts are already resolved and we are operating on purely internal register representation, we send that out to the scheduling blocks, which look at the resource availability at this particular instance, saying, look, multiplier can do 1 multiplication in 5 cycles, that's latency, and can launch it every 2nd cycle. And in this particular cycle, it is occupied, therefore this micro operation will have to wait for 1 additional cycle before it can go out to this particular execution unit. Right, and finally, we have the logical blocks that execute, that do what the instruction tells. So now we are coming to the characterization. If you look at the instruction tables, for example, this instruction takes 2 cycles, and this instruction takes 11 cycles. What is meant by that? That only the execution part takes that much. If we look at all the pipeline that we have described so far, we are, in practical terms, we are talking about 10 to 20, depending on a lot of factors, cycles before we even get to the execution. And there will be subsequent stages. So in all practical terms, to execute 1 instruction, it doesn't take 1 cycle. It takes on the order of 20 to 30. And this is true in isolation. So if you take 1 instruction and feed into the machine, it will take that much. However, there's a multiple stream coming in at every cycle, and at different stages within a pipeline, different instructions go through that, right? Therefore, there is a multitude of instructions in flight at the different stages, and therefore, it is correct to say that the execution will take like 2 or 11 or that many cycles. This is decoupled from the actual execution. Basically, the pipeline model, it kind of hides the overall end-to-end latency, And this is correct, because you care about the inter-instruction latency latency. And that, if you don't have any dependencies and conflicts, is a correct number. Multiplication will take 5 cycles, and 5 cycles later, you will have the results available that can be used by some other instruction that is, at this point in time, still hasn't reached the execution, but will at a time when the results of multiplication, as an example, are available. Execution is also the area of the pipeline that starts talking with the memory system. So there's load store queue, something that starts to deal with memory. That's prior to caching. There's also instruction cache, there's the data cache, they are different. And then the next one after that, all of the operations described beforehand, they were not externally visible, or at least they should not be externally visible. They were speculative. Because the processor runs ahead in time and tries to do something, thinking that it will do the right thing. Retirement actually finalizes those results and makes it externally visible. Well, not all of the externally visible events can really be eradicated. Well, you might have heard about all sorts of specters, meltdowns, and other things. Generally, talking to the memory system has remaining externally visible artifacts there. You can avoid them at a cost, at a rather large performance cost, and generally you don't want to do that. Well, maybe for some specific applications, and this is a question of software design. Right. Then we have the memory hierarchy, and finally we reach out our memory component, the part one that we have been talking previously. So this is saying that many of the contemporary platforms are out of order. Out of order, not in the sense that they are broken, but they execute things out of order. What's precisely out of order from an execution perspective? Not that much. Only the completely decoded and deconflicted operations that are fed into parallel execution resources. However, quite a lot of that is speculative. In a sense, all of the starting from fetching, decoding, and preparing for the execution is speculative, in a sense that it can be rolled back without mostly none of the externally visible effects. Talking about addressing. From a software perspective, the addresses that you deal with from the code perspective, they exist up to the boundaries of the layer 1 caches. Now, often there's a question, why do you have 2 caches and why they are so small? Well, if the cache is so good, why don't we have it noticeably larger? So first thing, why different ones? There are very different properties of accesses to data and to the instructions. Cache is also used as a temporary storage for basically markings, both for the instruction and for data. It stores different types of, say, internal service information. For the instruction cache, that's the length, the boundaries of the instructions, presence of flags, and all sorts of things. What we have been seeing in the decoding example, part of the outcome of that decoding is stored in the instruction cache. Well, in theory, instruction cache is read only. In practice, it is slightly writable, but not user visible, slightly writable. The attributes, which are not software accessible, they are written as the instruction stream is decoded. Now, the data cache is writable as well, but writable in a different perspective. It's about the cache coherency. It has certain identifiers notifying whether this particular line is exclusive to this core, is shared by the multiple cores, it has been updated by some other core and therefore needs to be invalidated and so on. Plus also the tags, the portions of the address translation elements that are required for logical to physical translation. And this brings in the second question, why cannot we make cache substantially larger? Well, not just increase it by another 2 kilobytes, but why we are not talking about a gigabyte size of layer 1 cache? This comes to a few aspects. First, that's laws of physics. In order to have more storage elements, you need more space. Therefore, it comes down to the signal propagation and signal integrity type of thing. Well, in theory, you can run around 20 centimeters per nanosecond. That's in theory and in ideal conditions. If you have multiple parallel wires, and you do in structures like this, you have wide data interconnect, you have a lot of addressing, you have the power networks. That starts to operate as a layer of capacitors, and that degrades the signal integrity parameters quite noticeably. Therefore, one of the limiting factors is how far you can reach from, for example, address decoders to the actual elements. And that limits the area, the layout of the cache a lot. The other thing is related to the logical aspects. Depending on how you implement your cache, either physically tagged or virtually tagged, if your cache is not, if the size of your cache is not proportional multiplied by the number of ways to the page size, you have two options in order to avoid the conflicts. Conflicts in the sense that the same virtual address will map, the same virtual address used in different address spaces will map or conflict with the same physical address. If your cache is physically tagged, you need to translate a logical address into a physical address once and then feed that into the number of comparators equal to the number of ways in the cache. This limits your cache size to the proportion of the page size multiplied by the number of ways. Right? And if it's an 8-way cache, you have 32 kilobytes and nothing more. If your cache is virtually tagged, then that means that you need to have the number of address translators equal to the number of ways. And that is a limiting factor. That means that you need to have a fast multi-ported memory only for address translation. And you will spend more time in translating and verifying tags than actually accessing the data. It's a balance. If you want to have access to layer 1 cache in a few cycles, in the fast cycles, you cannot have large area. If you want to have large amount of memory cache, you can, but you won't be able to access it fast. Right? We are talking probably on an order closer to like 7, 8, 10 cycles if the size of the cache increases, say, 4-fold. On the other hand, we cannot have a large amount of address translators for virtually tagged cache, because that also will take a large amount of area, and purely from a signal routing perspective, that will have to decrease, basically to increase the cycle time. And therefore, it kind of diminishes the amount, the value of the layer 1 cache. You have more space, but that space is accessible in a slower pattern. Therefore, the more practical way is to have a hierarchy of caches. For the most frequently ones, you have a fast one, which is rather limited, and limited due to both physical and logical properties, depending how you implement. It might be physically tagged, might be virtually tagged. That's purely a design decision. And then, once you get a notification that the line is missing, at the same time, even prior going to the layer 1, you actually emit requests into layer 2 as well. Again, it depends whether that's inclusive or exclusive or non-inclusive, different patterns. Right? But from a grand scheme of things, doing it this way, having a faster but smaller L1 and larger but slower L2, eventually will provide you the requested line statistically faster than having a layer 1 which is generally slower. Right, how we're doing with time? I think we still have some time, so let's move away from talking into seeing how this operates in practice. We have a very important function here. We have a function which does a very important task here. It verifies some condition and then does some bit shuffling. So basically, bit shuffling is a simple arithmetical operation. It's easy for the machine to do. And the branching is something that is not necessarily too easy to predict, right? So we have a call site which calls it with initially wrong parameter. So here's the code. We fetch a block, we find the length, we decode. Here's what goes into the execution. Now we have a branch. The second one is a branch. This is the first time we run this particular sequence of code. Therefore, there is no branching history. Therefore, there is a very simple rule. If the branch goes forward, it is not taken. If the branch goes backward, it is taken. That's basically done for loops. The loop goes back, therefore, it's an indicator that it is taken. This one goes forward, therefore, it's not taken. Right, so we fetch another block, possibly misaligned. We do some byte shuffling here and there at a cost maybe of one additional cycle. However, that's non-principal. We decode the things, we feed that into the execution, then there's an unconditional branch. That means that everything that we have decoded past this unconditional branch is no use for us. We throw it away and continue the process, fetching and so on. Eventually, this is a sequence of instructions that will go further down the pipeline into the execution. So let's try executing that. So we call that with a parameter 42, and eventually what happened, the machine, it doesn't know the outcome of compare to 27, right? That's still at the early stages of the pipeline, and there's a stream of instructions that is decoded. At some point of time, it will get executed. But right now, what is fed into the machine looks like this, and that's wrong. It has selected the wrong branch path. It will eventually go execute the compare to 27, say, oh, no, that's the wrong branch. Throw everything away, refetch, and redo it. This is normal. Basically, this is a mispredicted branch that resulted in us doing twice amount of work. Doing twice the amount of work is not the biggest problem. The biggest problem is that we have lost time. We have fetched from the wrong location. We did all of the decoding and then preparatory things, only to throw this away. Can we avoid that? Would be good. Let's see another example. We rerun the same function, this time with a different argument. Right? Same thing happens with decoding. We do fetch. There's a branch history saying, okay, last time called, this branch resulted in true or false. Yeah, last time present, so therefore this is taken. It cannot know the arguments for that. It's only looking into the history, saying, look, last time I saw this branch was taken, therefore I predict that it will be taken. The real-world branch predictors are far more complicated than that. There are multiple layers of them. They work in parallel. Some are faster, some are smaller. There's also kind of a conflict resolution scheme and all sorts of fascinating machinery. We are not going into those details. So we fetch another block decode. Here's another sequence of what gets in. Finalize. The branch is wrong, right? So it was wrongly predicted, right? Flush everything and restart from the beginning. So some upcoming platforms start to implement the functionality of fetching both ways. That means that if C is a branch, it starts to fetch the instruction stream both for the taken and non-taken branch. The reasoning is very simple. We have enough of the execution capacity, we have substantially enough of the decoding capacity, but we cannot predict the actual execution without looking at the data. Therefore, we will try to look into executing both branches. Right? Therefore, there are two sequences of instructions coming in. They are marked simply as depending to different branches. Eventually, they go to the execution, and both of them might get executed. The results or the outcome of one will be thrown away. The results of the other will be finalized and then sent to the retirement. Now, if we actually look what the Smarter compiler did, Smarter compiler removed the branching completely. It's simply, and again, at the cost of doing twice the work, right, we avoid branching here. So can hear our neighbors at the adjacent room clapping victory. So they finished the session slightly earlier. We'll probably spend some more quality time looking into our intricate details. Memory copy. The functionality that you have to use really often, and you better be efficient with that. So one of the problem spaces with that is that there's an alignment or misalignment of source, possibly destination, and then the relative alignment of the two. You can do multiple ways how to implement memory copy efficiently, or you think that you can implement that efficiently. Scale away, unrolling, vectorization, whatnot. Plenty of possibilities. Let's take a look at a very naive way, right? We just do a byte copy and not efficient from implementing, basically from a resource availability perspective. The machine will do certain things to try to optimize at least the memory operation. If, for example, if you are copying a 16-byte buffer with this implementation, there won't be 16 memory operations. In all essence, there will probably be one. That will be combined. But purely from an instruction stream perspective, that just doesn't look practically rational. Well, if you let a little bit more freedom to the compiler, it might want to auto-vectorize that. This certainly works. The logic is very simple. There is basically precondition. If we fail that, we do in a scalar way. If not, then we can try run that as a vectorized. And the benefit of that is that the cost for encoding, cost for decoding the relatively longer vector-based instruction results in way wider actual operation, right? So we benefit from an instruction density point of view. Now, we might take a look at, and this is actually a practical example from a ClickHouse. They tried to implement their own memcopy in their way, and that's not too short of the implementation. Basically, again, vectorization plus some preconditions. It results in something like this. It certainly works. However, the open question is, from a software perspective, you certainly cannot have the full visibility into the platform state, right? How source is aligned, how destination is aligned, what is the cost of the current memory operations. You don't have visibility into the memory hierarchy, content and operation. What if you had basically a micro-coded sequence which does precisely what certain selected branches of memory copy would do? Yeah, certainly. One single instruction which launches something like subroutine on a microcode level, which verifies whether this is aligned to that, this is aligned to that, and just selects the best possible option and goes forward. Certainly it works. Is this a universal solution? No, not at all. You can play with micro benchmarks. Micro benchmarks probably will show that this is amazingly, blazingly fast. However, micro benchmarks lie. You need to do the proper benchmarking in order to see whether this is a reasonable solution. Right, we need to speed up because I can already hear coffee outside. Right, hashing. This is a nice candidate to show how out-of-order operation can and does operate. Well, internally it allocates a set of 3 separate registers and reorders them, runs out of order, does out of bounds, and other bad things from a software perspective. However, on the hardware side, that's absolutely normal. This is basically an example showing how the compiler can help or actually do harm if it doesn't see enough of the code, and then what would happen if you actually rearrange your data structures. And the outcome of that is whenever you can fix the problem with data layout, try fixing that. Eventually it will help far more than trying to implement fancy optimizations and invent your own algorithms and things like that. Right, we are coming to a conclusion, measuring the performance. measuring the performance is certainly fun. That's a rather complex area where you need to understand not only from a software perspective what is happening there, but also your underlying platform. The platform there is to help. A lot of performance monitoring functionality is available in contemporary platforms. Just use that, right? Not all of that is, say, too publicly documented, but with certain level of NDAs, you can get vendor documentation, and that definitely will provide you a lot of the insight of what is happening there. Vendors have definitely sufficient and usable tools for doing these types of micro benchmarking, highly recommended. Now, the important aspect, don't try to modify more than a few parameters at the same time while doing the end-to-end measurement. That's one of the common problems seen in the field that, right, I have a performance problem, therefore I change this, change that, and yet that, and then rerun the benchmarks, and the benchmarks look the same, although many things have changed. And you're missing the impact of each of those changes. Universal ISA and vectorization. Well, actually, there will be a whole other session looking at the agenda about the vectorization. Therefore, we will skip that, and we will move into the discussion. Right? Questions, suggestions, thoughts, gifts, bribes, anything else? Yes. They stay in the cache, not in the memory. They are all the time. They are all the time in the memory. Yes, those are side channel effects, right? Again, memory is not that transparent. If you touch it in some other way, even if the compute platform, basically, even if the processor is trying to fetch that, you will modify the state of the cache. You can implement it this way that it is cached, but only temporarily, right? And not visible after this, once this instruction is not yet retired, right? So if you fetch something that was on the wrong path, and then later you realize that it was on the wrong path, you can, well, hypothetically, you could indicate that you need to flush it out, right? But you obviously can imagine at what performance cost that would come, right? Therefore, you would need to look for other solutions, right? That, that information is not leaked by other things. Yes, so I'm getting kicked out of the stage, right? So I'll be here around. The questions we can discuss afterwards. Right, thank you.